We're ready to start Chapter 30, Section 3 now. That's all about magnetic flux. That chapter is in your textbook, the night textbook, pages 842 to 844. So I would recommend you have a read through that section. Also, if you don't quite remember electric flux, so the E.dA stuff that we used in developing Gauss's law, if you don't quite remember electric flux, I would recommend you go back and you just review that electric flux, what it means, the number of electric field lines cutting through an area, and the fact that it's a scalar. So just have a quick look through. As we're going through the rest of this chapter, I would ask you to keep in the back of your mind, can you use the things we're going to discuss to describe how a transformer works? So let's have that as a goal of this chapter. So as a very quick refresher about electric flux has a symbol of phi with a subscript of E. It's the integral of E dot dA. If your area is a constant and your electric field is constant, or if it's not in some sort of very odd shape, then your electric flux boils down to E dot A. And your electric flux is a quantity representing how many electric field lines cut through a surface. Electric flux can be positive or negative, but be careful not to assume that it has a direction. So the electric flux is the scalar product between electric field and area. Because it's a scalar product, electric flux is a scalar. So positive or negative just show, are the electric field lines parallel to the area or are they anti-parallel? That's what that sign means. It's not a direction of flux, even though a lot of textbooks talk about the flux in and flux out, but that's not really meaningful. Magnetic flux is going to be the same deal. It's a quantity representing the number of magnetic field lines which cut through a surface. If you take a loop and view it from the side, so this is, let's say, a circular loop, and if we put it in a magnetic field that moves to the right, we get a lot of magnetic flux. So we get a lot of lines cutting through the surface. If we put it at an angle, we get fewer lines, and if we put the loop exactly parallel to those lines, then no lines cut through it. So the magnetic flux is the integral of magnetic field dotted with area, or if we have a simple magnetic field and area, then it's just B times A. The scalar product between B and A. Like electric flux, magnetic flux is a scalar, so it does not have a direction. It has units of the units of magnetic field times the units of area. So the units of magnetic field are Teslas times meters squared. I'm writing this with my touchpad, so it's not that easy. Teslas times meters squared is also called a Weber, WB for Weber. Your book tends to use Teslas times meters squared. I like Weber just because if I had a unit named after me, I wish people would use it. And then our pictures here, like we already discussed, they show how the flux changes depending on the orientation. So let's make sure we know the direction. We know what the direction of the area vector is. An area vector is perpendicular to the plane of an object. So in this case, the area vector would point straight. Oops, that wasn't very good. Can I erase it? Yeah, there we go. The area vector would point straight out of the surface. So there's the area vector for this guy. When the magnetic field and the area vector are parallel, you get the biggest flux. When they're at the angle, you get some flux, and when they're perpendicular, like this, you get zero flux. So the area vector is perpendicular to the object itself. One thing about area vector, and we'll discuss this as we go through, in the first picture, the one on the furthest left, I drew the area vector to the right. I could have just as meaningfully drawn it to the left. You can't really tell if it points to the left or to the right. On a closed surface, the area vector always points out, but if you just have a 2D surface, you don't know which way is out. So when you're doing these problems, you always have to show your area vector just to define which way you're doing it. Okay, so we'll move on to some examples of magnetic flux next.